Swayam Prabha. Digital India. Educated India.
Okay. Now, PL0 has the highest privilege. PL1, PL2, PL3, this is the user. So, many of the operating systems that runs on x86 architecture will take all these 3 privilege levels as supervisor mode and this as user mode, right. But actually you can do much more classification there, it does not exploit these 3 modes then. But anyway, PL0 is, it will actually go to PL0 for supervisor and PL3 for user. It will not use these many, I am not seen any Unix code which uses PL1 and PL2. So, the processor itself will work in 4 privilege levels, privilege level 0, privilege level 1, privilege level 2, privilege level 3. Okay, you understand, right? Let us talk about PL0. This is highest privilege. There are certain instructions that could be executed only by privilege level 0 code. Those are called privileged instructions. This will be executed only by a privilege level 0 code, no other fellow can execute this. If I am a privilege 3 code, I can't do it. You getting? So, this is privileged instructions. Okay. So, these 2 are very important for us to understand PL0, these 2 are very important. While PL3 is lowest privilege and it cannot execute any of the privileged instructions. Only PL0 can execute PL1, PL2, PL3, none of this can execute privileged instructions, okay, right. So, let us have the notion of what a privileged instruction is, right. Okay. Now, what happens is as follows. Now, when the system comes up, operating system comes up, in your memory, it creates a table called a descriptor, segment descriptor table. Okay. This segment descriptor, when the operating system comes into existence, it creates a descriptor table, it is called a segment descriptor table. Please note this carefully because I am going to talk about security here and this is very, very important. Now, this descriptor table will be starting from some point, okay, and that point is pointed to by a descriptor table register, DTR, where it starts, that will be stored in a descriptor table register, okay. You are able to understand what I am saying? Now, in the descriptor table register, what I will store is for every segment that I am creating, I am the operating system, right. In the descriptor table, what I will do is for every segment I am creating. So, let us say P0 had code stack data, P1 had code stack data, P2 had code stack data, P3 had code stack data, okay. Let us go a little back and see where were they. So, 1000, 1290, 1090, 0. So, something I will just add 1000, 1000, 50, 1090, 20, 1000, 100 comma 40, this is 1200, not cross, right, 1200 comma 50, 1270 comma 30, 1300 comma 40, so 1400 comma 100, 1500 comma 20, 1550 comma 30, 1600 comma 100, 1700 comma 10, 1750 comma 40, something like this. So we are all the segments. So whenever the process P0 came into existence, immediately your segment descriptor table, the operating system, what it does is it allocates that memory. What it means by allocating that memory, it will just put, so let us so this descriptor table has several descriptors, so let me say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so 9 descriptors. So when P0 came into existence, you would have put 1000 here and 50 here limit, and it will say this is a code segment, okay, and it will give you a privilege level. So this is a 3 process, operating system is executing, it will give you a privilege level 3, this is user process. Let me say this is user process privilege 3, this is also user level, this is 2 and this is all are 3 user, okay. Then it will create another 1090, 20, and this will say this is a data segment and privilege 3. Then it will say 1100, 40, it will say stack, and then it is 3, okay, stack segment. So let us just fill it very fast, 1270, 1300, 50, 30, 40, CS, SS, this is SS and DS, sorry, CS, SS, DS, 3, 3, 3. Thousand 400, 1500, 1550. Okay. Okay, now 100, 20, 30, CS, SS, DS, 3, 3, 3, and so on. Okay. Now this will be stored in this. Okay. Now there will be some one thing for the operating system itself. So let me say this starts at 0 and it goes on till 900, because your 1000 all your, so first part is loaded by the operating system. There will be one data segment for the operating system which will say I will start from 0 and it will go till 900 and say this is data segment, and this will be privilege 0. Okay, it will be privilege 0. So the operating system, when the operating system is executing, let me say forget this P3, when the operating system is executing, its data will be from 0 to 900, okay, let us say limit is 900, and code will be from 900 1 to say 900 to 950 or something like, stack will be from 950 to 1000, and your remaining. Let us assume that this is how the operating system, very simple small operating system. So when the OS is running, suddenly one process comes up, I want to execute, A dot out comes, so the OS gets initiated. Now it will go and allocate 1000, 1090, 1100 in the descriptor table. Okay. Now, so what will be stored in CS? It will not store 1000, 1050, rather it will store 0. In DS you will store 2. In SS you will store 1. When P0 is executing, right, I will not store the base, limit, etc. what I am going to store there is the selector. So, this essentially, rather than calling this as a segment register, I will call it as a segment selector, because it selects from the descriptor table what segment I need. You are getting this? Are you able to follow? I select from the descriptor table what I need. So, here please note that 1050 CS3 is stored where? In the descriptor table. So, when I start executing, in CS I will put 0, in DS I will put 2, in SS I will put 1. So, the moment somebody wants to access data, it goes to 2, the entry 2 here, there it finds the base address 1100, then it will also check if the offset is more than 40. If it is more than 40, it will say this fellow is doing something wrong, it will raise an exception, and then it will start executing. So, instead of storing the value 1100 in DS, I store it in a table and I make this point to a table. Now, what happens when P1 comes to execution? Your CS now will become 3, DS will become 5, SS will become 4, right, basically these 3 segments 3, 4 and 5. So, when P1 wants to access data, what will happen? It will go to 5, in 5 what is the entry? 1300, and that will be treated as a base, and there it will go and check if I am going to access anything more than 40 bytes from that price. If it is going to be, it will raise an exception. So, what happens is, right, I can basically go and access these values. Okay. Now, other than this value, so what the most important thing is that I cannot go and change anything here as a user process like P0, right, as a user process P0. Can I go and change anything in this segment? If I want to go and read or write from this segment, I have to put some offset address, and that will get added automatically to my segment base. So, even if I want to access memory, I will put move some address here, right, I have to put that. This address automatically will get added to your data memory. If as P0, right, my data memory is 1100, it will get access to 100, and if it is greater than or this 140 bytes, then automatically it will say sorry, it will not even allow you, right. So, if I want to go and change any of these values, suppose I want to go and play with this table, suppose I want to go and access say P2's data, right. So, essentially I have to go and make this as this limit as some 600. If I make this limit as 600, then I can basically go and play with the data. But if I want to change this to 600, then what should I do? I have to go and access this and change it. I can't access this, right, because I am restricted to accessing these.
Are we not allowed to be modified or even read?
I can't even go and see, I have to go and change this, no. It depends upon whether it is a read only segment or a write. If it is a read only, if it is 0, this is privilege 0, first and foremost I can't come to this at all. After that only I can go and change. The other thing is, what I can do, I can go and change this descriptor table register. So, this is descriptor is stored at some 600, okay. Right. This is 600, from 600 onwards this descriptors are stored. Suppose this 600 I will make it as 509, 500, I will get some space here 500, and there I will add my own descriptor which will start at some 0 and go to 4 GB with DS, and I can go and play with it, correct. So, for doing that, what should I do? I should go and change the descriptor table register. So, there is a command called LGDT, load global descriptor table register. This LGDT is, and you give some arguments to this, PK will teach this in great depth there. right. What will happen is this LGDT will go and update this register. So initially I had this as 600 and from there this entire table was stored. I can, for me to change it to 500, I have to execute a command called LGDT, right. And if process 0 wants to go and execute the command of this fellow LGDT, process 0 is at which privilege level? 3, right. Now LGDT is a privileged instruction. Privileged instruction means who can execute LGDT? Only a PL0 code can execute, right. So the process cannot go and change, the P0 cannot go and change the value of the base of the descriptor table and add its own descriptor, because this LGDT is a privileged instruction and only privilege 0 code, in our case the kernel, can go and touch it. So when a descriptor table is fixed with privilege 0, then what happens? Nobody can change it, only the kernel can go and change it, right. And for me to go and change anything within the descriptor is not possible, because I will not be permitted. As P0 I can only access 1100 to 1139, anything more than that I will catch. For me to access anything more than that 39, I have to go and change the entry in the descriptor table. I cannot go and change the entry in the descriptor table, right. It is a chicken and egg problem. So to change the entry in the descriptor table I need permission. To have the permission I have to change the entry in the descriptor table, and I can't go and add my own fancy descriptor, because that LGDT basically tells me where the descriptor starts and I can't go and change it. And also there is a limit here. LGDT will give you the base of the descriptor table and also the limit. Limit tells how many segments currently I have. I can't go and add more segments. So currently I have only 9 segments. So this base will be some 600 and the limit will be some 9 or some multiple of 9. Okay. Now I can't go and add more than 9 segments, 9 or 10. Okay. So 10. I can't add more than 10 segments. Okay. So I will not be in a position to create a new segment descriptor, nor could I basically access. So you are able to get this? Okay. So this is one part of the story. So now the first thing that we will understand, there are a lot of doubts, I will come to those doubts, but please understand here that my segment register essentially stores a selector, which is nothing but an index into a descriptor table, and my descriptor table basically stores the descriptor table register basically stores the start of the descriptor table, and the value of that start, that register, can be changed only by a PL0 code. And what is stored there would be 4 things for every descriptor: its base, its limit, what type it is, and then what privilege level it is. Basically it is describing the segment, it is giving the attributes, like your name is so and so, your roll number is so, this course. It is basically giving you the attribute. That is why we call it as a descriptor table. Now as a process I can access only any data. So what is the privilege level of a process? For every, so I am executing from some, so I am executing code segment, right, code segment 0, when P0 is executing code segment 0, that code segment 0 has a privilege level 3, so that is the privilege level. So whenever I am executing, my code segment register, CS register, has a selector that will be pointing to some entry in my descriptor table. That entry would be basically a code segment, type code segment, and it will have a privilege level, and that is the privilege level. So that is also called as CPL, current privilege level. So initially your operating system will be executing, its privilege level will be 0. When the context switches to, that means when the context switches, this CS register will be loaded with this segment, DS with this, DS, then what will be the privilege level now? CS segment points to 0, the privilege level now becomes 3. When P1 comes into existence, now the CS register points to 3, selector 3, and that has privilege level 3. So that's how, right. So as you go from one process to another, each process when it's executing will have some selector in the code segment, otherwise it can't execute, okay. And that code segment has a selector, and that selector will have automatically a privilege level. It will actually point to some descriptor in a descriptor table, and that will have a privilege level, and that is the privilege level of your process, okay. So what we will, so there is one more very important question that we need to answer, but that we will reserve it for next class. But today what we do in assignment 1 is that we will now work with privilege level 0 code. You are the kernel, okay. So you execute everything as a kernel mode, right. So we will only write privilege level 0 code, but in privilege level 0 I want you to set up a descriptor table. In that descriptor table I want you to add a lot of descriptors, DS, CS, SS, ES, FS and all, and we will give you a program in which the data will be stored, your code will be stored in some segment, data will be here in them. You have to set up all those, you have to set up this GDT, you have to set up your GDTR, and then you load your program and start executing it, okay. That is what you will be doing here. So essentially what you are learning is that you will be given a problem for which you will write an assembly, you write a C code and then translate it into an assembly code, that will be easy for you. You understand some amount of translation from a programming language to a assembly language. By this you get a good grip on what? A good grip on assembly language and translation basically. Once you get this, we also, when the program has to go for execution, when it goes and says the operating system, hey, allow me to execute, what are the steps done by the operating system? You are going to do that manually. You are going to create a code segment, you are going to store a data segment, stack segment, that you are going to load it, you are going to, already you will have your descriptor table register pointing somewhere, you are going to load these values and then execute the program and then show the results. So essentially when a program wants to go and execute, what is the architecture support? We are not writing operating system here, we are just trying to understand how the architecture will support this, and that part we will do it today, okay. So as we see, we will do it in the first assignment. So there are a lot of benefits of segmentation. So these two, not fragmentation of course is, I have explained what is fragmentation. Intra-process protection we will do in the first assignment itself, while inter-process protection and security we will do it in the fourth assignment, okay. So the first assignment would be on the segmentation, the second assignment would be on interrupt service routine or exception handling, the third would be on virtual memory, and then the fourth will be on task switching. So we will do all these 4 assignments. And the next thing is that you will never be given, if you are continuing on system building, next generation is going to be on mobile phones and IoT devices, you will never have such a fancy debug environment, understand. So a lot of time you have to do from scratch. So imagine writing an operating system without a debugger. Operating systems have to be written without a debugger. Why? Because debugger runs on top of the operating system. You do not even have an operating system, how will you have a debugger? So imagine writing everything by just seeing some 7 segment display and finding out something is working or not. See, look at that. So this type of a very careful development, lot of time you will fail because you do some silly errors. So this will make you very, very attentive while you do programming. So lot of benefits do come from this, okay. So please take it in that spirit, and I want you to work on this, okay. Now doubts. Somebody had a doubt? Yes, Jnanambika, yeah.
In the descriptor table, how does one know that 0 is stored for process 0, I mean 0, 1, 2 is for process 0, or is it for process 1?
Exactly. So the operating system will maintain this bookkeeping, okay. The operating system will maintain this information for which process what is, so it maintains something called a process control block. You will be learning that in assignment number 4, okay.
So descriptor table is itself used for bookkeeping, and there is also a bookkeeping
for every process. Yes, unfortunately a lot of book, really 104 different entities have to be stored, 104, 104, okay. and at least 3 or 4 of them are pointing to books. Book in the sense this type of information management. Okay. So that is what it means to write an operating system. So yes, this is a very good query. I need to maintain information about processes. So there is something called a process control block. In operating system we call it process control block. In architecture we call it task state segment. Okay. Process control block is the language of operating system. This is equivalent to what we call as task state segment in architecture. Now these two. Okay, now about this you will learn in assignment number 4. How we can do this bookkeeping, etc. We have some doubts. Gyanambike.
Is there any way the user process can manipulate the selectors?
Is there any way by which the user process can manipulate the selector? Yes, user process can load selectors. We are going to come to that in great detail. That is one question that is unanswered, but then we will do it in assignment. Next doubt?
Is there any virtual machine there in this?
There is a virtual, no, as of now I have not talked about virtual memory at all.
Virtual machine there.
Virtual machine, there is no virtual. We are now working at the hardware level. We have crossed the virtual machine. We are now taking assembly code and executing on the processor. So essentially coming back, the difference between what you did as an assembly language that time, right, in your 3rd semester and this is, there we were concentrating on things that are important for executing your program, correct. We never talked of anything that is important for the operating system. So a lot of operating system, our view was that it gave us a library of functions and we used it. You remember the assignment, right? Don't forget it, man. You all told it's tough. Tough means it should be in your head, that's what. Okay. So right now when we go in, what we are going to see that the compiler part that is there already there. So we just gave you some tutorials and then you can follow that. Now I know how you can translate it, translate a normal program into assembly. Lot of concentration now will be on those type of machine language instructions which are going to do functionalities related to operating system needs. So that's the new coloring. There is no need for me to come and sit in a BTech Premier Institute 4th semester and say mul AX comma BX will multiply AX into BX and store the answer in AX. Okay, that's shit crap. Okay, I don't want to do that. What that anybody can understand, you can understand. What we need to understand here is that how this assembly instructions will help lot of things on the operating system side. So as you see, the coloring is going in that way, right. We are talking more about OS fundas rather than code compiler fundas, right. That is very important here.